I'm going to try to show you how an interferometer actually detects gravitational waves. If they are propagating or if they're heading in the direction of this blackboard, they will do along let's call this the x-axis. They will stretch the x-axis, and space-time in the y-axis will shrink. And a little bit later, do the opposite. And we're going to exploit that property of gravitational waves. That's called the polarization of the wave in this device, which we call the interferometer. It sends out a light beam, and the very first thing it encounters is a beam splitter. It's a device that transmits light, about half the light that hits it, and also reflects light, about half the light that hits it. This beam got reflected from here, went up, got reflected inside this jazzy mirror, which is this corner, and comes down to here, and here it gets reflected back to the source. But another thing that happens to it is it gets transmitted as well, so it comes down like that. But there's also a line that comes this way. Light hits this thing and also gets reflected. They both get reflected together and come to a photodetector. Here's the photodetector. And remember what happens with light waves. When they propagate, let's say in this direction, they have electric fields that go up and down. They wiggle with the light wave. As a wave, this is negative electric fields, that's a positive electric field. That means the electric field points up, here the electric field points down, that's all. And the amplitude of this is the size of the electric field. You imagine this whole pattern zipping along to the beam splitter and then zipping up to this mirror and then zipping down and hitting the photodetector. It's the same thing happening along here. That entire pattern moves along, moves up, comes back to the beam splitter and goes down to the photodetector. But this time, it's reflected by the beam splitter that flips this whole thing over, just flips it over. If you have set the thing up properly, namely this path length is the same as that path length, you can make it so that the photodetector doesn't see any light whatsoever. Now, let's put in the fact that the gravitational wave comes along and stretches one side and shrinks the other. When I add these two, this one and that one, I don't get zeros anymore. Now, there is light hitting the photodetector. And that is the basic idea. A gravitational wave comes along. It destroys that difference between the two paths so that we no longer have just zero light, we get light. And so we have converted the gravitational wave into an amount of light that appears at the photodetector. And that is the fundamental idea behind the measurement.